In our last video, we left off talking about all of our linear stuff, all of our tables and all of our graphs and word problems and equations. Well, so let's talk about them. The first thing we can look at for our linear relationships are tables. Now, tables are just a visually or numerical way to organize simply just the data points. When you see a table, X and Y, or in our Sally case, it's time and money. After 0 hours of work, she had $33. After 1 hour of work, she had $47.50. After 2 hours of work, she had $62, and so on. It's a visual way to see all of the data points. Each of these is a different ordered pair. Again, it's just a data point that you could put on a graph. So from this table, the things that we already know for sure, points, just a bunch of points. Now for lucky, they might give you a couple specific points, the y-intercept and or the x-intercept. And in this one, they gave us the y-intercept right here. When our x value is 0, that would be our y-intercept. So they gave us a bunch of different points, including the y-intercept. Things you might need to figure out on your own, again, just looking at all of these values, we can figure out the constant rate of change, or the slope. Now I'm going to show you how or why we can do this. You can just simply look and say, okay, my independent variable, this x, is changing by 1 each time. So for slope-wise, that would be a denominator of 1. So all I'd have to do is figure out how much this is changing by. Going from here to here, it's going up by 1450. So 1450 over 1. 1450 over 1. 1450 over 1. Right here, we make a little jump, though. Let's check and see, just using these two random points. Didn't have to be a change of 1. It can be any old points here. Let's see the slope. 3 hours, and she has 76.50. 7 hours, and she has 134.50. Well, the independent variable went up by 4, from 3 to 7, 4 more hours. The dependent variable, the money, went up by 58. She got 58 more dollars in those 4 hours. So our slope would be 58 over 4, change in the y over the change in the x. Divide both of these by 4, this can be reduced to 14.5 over 1, or just 14.5. So we can see any 2 points. I don't have to only do these easy ones. I can even do one like this where they're 4 apart and 58 apart, or where they're 6 apart, or where they're 27 apart. I can use any of these to figure out my slope. This is a constant rate of change, and all of those changes are proportional. One thing to note, though, we're looking for the change. 58 and 4 were the change. Notice there wouldn't be a spot where my x is 4 and my y is 58. Okay, because of that extra constant, we don't have 4, 58. Okay, you can't use the actual x value and the actual y value, because if you look here at your y-intercept, 33 over 0, well, that would mean that there's a slope of 0. Right? It doesn't really work that way. We can't have, actually that would be undefined. Anything divided by 0 is undefined. We can't do the values over the values. It's the changes over the changes. There's a big difference there. So, if we are given a table, what can we do with that? Well, if a table's just a bunch of points, you could graph them. You could plot them all out and see where they lie visually. If they happen to give you points and you figured out the slope, you could do point-slope equations. And you can even figure out a word problem. Okay, if they give you that your x is changing, again, time and money, you can figure out a word problem that goes along with time and money. I know I just said the point-slope form, but if you're lucky enough and they give you the y-intercept, you could also figure out slope-intercept equations. So from tables, you can figure out a lot of different things. Now, your job from here on out is to be able to figure out what you want to be making with these. If you are given a table, you should know I can make any of these things. What do I need to make in my problem? If we are given graphs, graphs are just a visual image of the constant change between two variables. Now, this doesn't necessarily fit with our Sally thing, because hers started at $33 and mine isn't way up at 33. But again, we can just kind of see there's a constant change. As our x variable changes the same amount each time, our y variable is going to change the same amount each time. Okay, constant rate of change makes linear change, which graphs a perfectly straight line. So, from any graph, you should be able to find points, like here is a point, or here is a point, or here is a point, or here. You should be able to look at this and say, well, I have a bunch of these points. What could you do with those points? You can make a table. Once you find the slope, you can use a point-slope equation. You can do, again, if you find that intercept is one of your points, you can do a slope-intercept equation. You can do a lot of things, but you'll have all of these points to use. You can even use a random point like this as your x and y value plugged into one of your equations, just to check things. All of those are possible from this graph. Now again, if you're lucky, like we are here and here, your graph might happen to give you intercepts, kind of only if you're lucky. They won't always be good, perfect intercepts, but in this case, we can see they actually are. Given all of these points on the graph, one thing that you might have to figure out is the slope. So from a graph, we're going to definitely know points. With 2 points, you can find the slope either visually up 3 over 2, up 3 over 2, or we can just use the 2 points and do y2 minus y1 over x2 minus x1, and we can find the slope that way. So it gives us points, gives us the slope, and maybe even gives us some intercepts. What can we do with all that information? Well, you can go from a graph into a table and just make a bunch of those points in your table. You can make a slope-intercept equation if they were nice enough to give you the intercept, y-intercept, and you figured out the slope. You can write a standard form equation if they gave you both the y and the x-intercept. You can write a point-slope equation using any of those points and the slope. And you can even go back into a word problem again if you know what your x variable is talking about and what your y variable is talking about. If you have a label for those variables, you can make a word problem from it. So again, from a graph, you can make a bunch of different things. Word problems. Any word problem is just a verbal description of the scenario. So I'm going to show you a couple different examples of what word problems could be. So for example, if they said, the hot air balloon is climbing 135 feet every 2 minutes. After 26 minutes, it is 1,800 feet high right now. Well, okay, it looks like what can we measure? Feet, or height there, and minutes, or the time. Which one is affecting the other one? Well, after so much time, you would be so many feet high. So it looks like minutes are going to be your independent variable, and the height here in feet, that's going to be your dependent variable. Your feet, or your height, depends on how much time has gone by. Okay, they've also told you enough information. They said after 26 minutes, it is at exactly 1,800 feet. So they gave you a slope. They said, here's your rate of change, 135 feet per 2 minutes. Change in y over change in x. Change in your dependent variable over the change of your independent variable. They also gave you a data point, or an ordered pair. They said after 26 minutes, it is 1,800 feet high. So we know somewhere on the graph, or on the table, there is this point 26 is your x value, 1,800 is your y value. So in this little word problem, slope and point. So they could definitely make a point-slope equation. Since they gave us this one and this one, we could write an equation from this word problem. Or we could make a table, starting with this point and filling in all the x values every 2 minutes, so 26, 28, 30, 32, 34, and then starting with this 1,800 and just keep adding on 135. So you would fill out a table using this one point and this slope, which again is just your change in x and change in y, and you could figure out a bunch of other points. With all of those points, you could make a graph then. So just from this one word problem, you can figure out a lot of different things. Even from that point-slope form, you could change it to a slope-intercept if you wanted. And that could help you make the graph. So enough information is given here to figure any of that other linear stuff out. And it's kind of on you now to be able to figure this stuff out and use it how you need to. Another example. Let's go back to our Sally example. Sally has $33 and she works for $14.50 per hour. Well, they give you a y-intercept. Again, that's like your starting point or your constant of $33. They give you a slope, a rate of change of, oops, I never changed that one. This should not say that. It should say 50 per hour. Slope or your rate of change is 1450 per hour. You started here, so you can make a slope-intercept equation. From that slope-intercept equation, you could graph it. From that graph, you have all those points, you can make a table. So again, you have enough information here to figure out any of those other things about linear equations, or linear relations. Here's another interesting example I want to talk about. In this case, we're still talking about two different variables, pop and chips. So if pop costs $2 per bottle, and chips cost $3 per bag of chips, I guess, and I have $36 to spend. If we think about this in real life, if I buy more pop, well, I can't get as many chips because I only have the $36 to spend. If I'm buying more chips, I can't buy as much pop. So these do definitely affect each other, and they affect each other at a proportional rate. So I'm going to make a quick table from this information, and we're going to talk about what this all means. I'm going to call the number of pops that I buy my X value, the number of chips that I buy my Y value. So at $2, I could buy 18 pops and still only spend $36. But that would mean I couldn't buy any chips, so 18.0 is a point. I could buy no pops and then buy 12 bags of chips. 3 times 12 is 36. So 18.0 and 0.12. Those are a couple data points I could make. Okay, I could also decide I want to buy 3 bottles of pop, so $6 in total, and 10 bags of chips, so $30 total. 6 and 30 makes 36. So this would fit us well, 310. I could decide, okay, I want to get 6 bottles of pop, so $12, 8 bags of chips, so $24, 12 and 24 also makes 36. Another example, I can go 9 times 2 is 18, 6 times 3 is also 18, 18 plus 18, 36. So I made a couple of quick things on my table here, just a few data points, because I wanted you to notice something here. I'm calling X the number of pops. I'm calling Y the number of chips. As I look down my table, the number of pops that I buy is increasing by 3. At the same time, the number, we're starting right here, by the way, increasing by 3. The number of chip bags is decreasing by 2. So even though y had to do with chips, and chips cost $3, this 3 was actually affecting my x value. This 2 was actually affecting my y value. So even though we say the cost of the x value, or the independent one, was $2, that $2 actually affects is the change in the dependent variable. The cost of the y value, or our dependent variable, is $3. That actually really affects the change in the the independent variable. Okay, $3, this was going up by 3. $2, this was going down by 2. This 36 is a constant. We will always have that just $36 to spend, but it is not quite my y-intercept. I'll show you how or why. So they gave you enough information here that you could make a linear relationship. I just did with a table. I'm going to show you some other things you can do. Like we said, if pop costs $2, we can say 2 times x, 2 times the number of pops that we buy. If chips cost $3, we can say 3 times y, 3 times the number of chips we buy, equals 36. Money I spend on pop plus the money I spend on chips equals the money I have in total. This is a standard form equation. So this word problem, the way it was given to us, we can make a standard form equation from that. ax plus by equals c. Let's work at getting y alone in both of these cases. We're going to mirror it. What I do on this side is say minus ax minus ax. So what I'm going to do over here is minus 2x and minus 2x. On this side, it means that we have by equals negative ax plus c. On this side, it means we have 3y equals negative 2x plus 36. On this side, that means we need to divide by b. So I divide by b on both of these. Same thing over here. We divide by 3. I divide both of these by 3. It's kind of like distributing. What this leaves in the end is y equals negative a over b times x plus c over b. Notice this is really similar to y equals mx plus b. Here is a slope, here is a y-intercept. Now you might think, hold up, that c value was 36. That was a constant. How come that's not our y-intercept? Well, it should make sense. If we look over here, your y-intercept is 12. You can get 12 bags of chips and no pop. Here, we found our 12. We did 36 divided by 3 to get 12. It's the same as saying c divided by b. So up here, our constant divided by the cost of the y, that would give us our 12. Now over here, when we got y alone, we ended up with negative 2 divided by 3. Here is our slope, our m value. Now where does negative 2/3 come from? Because we're talking about change of the dependent variable, change of the independent variable, cost of x, cost in y. Where did all that come from? Well, look over here. Change in y, negative 2. Change in x, positive 3. Negative 2 over 3. So, this word problem did in fact give you all the information you need. Gives you the cost of x, cost of y, and a constant. This is enough to make a y equals mx plus b linear form, and ax plus by equals c linear form, or a table. So you can make any of those from that one word problem. Last example of a word problem, in 1960 the tree was 3 feet tall, in 1965 it was 3.2 feet tall, in 1970 it was 3.4 feet tall, in 1995 it was 4.4 feet tall, etc. This is just giving us a bunch of data points. Now what can we do with all of these data points? Of course we can make a table. Also going from here to here, I can find the slope. With a point and a slope, I can make a point-slope form equation. From a point-slope form equation, I can make any other equation. From any of those equations, I can make a graph. You can make anything. So, again, using these word problems and picking out what exactly they're telling you, you should be able to piece together any other linear form you need. So a word problem, you can get tables, you can get graphs, you can get equations, depending on what they give you. Again, it is your job to make sure you know what they are giving you in the word problem, or in the graph, or in the table, or in the equation, and think about how you can fit that to the other pieces. The last thing that we've been talking about is equations, but we've already gone over the equations. If you have any questions, make sure you're asking them. Otherwise, I'll check you later.